Hi everyone, I'm going to be going through the composite trapezium rule. Hi everyone, I'm going to be going through the composite trapezium rule today. I'm going to start by looking at how to do it when you're given a set of data, and then I'm going to do a question where we're given an accuracy we need to work to. The main things you need to do these are the key formulae, which should be in your notes, and I'll be going through those as we get to them. But for this one, because each of these are basically going to be exactly the same as each other, I'm going to just do the one, and it's the same process for the rest. So let's get started. Starting off, it's pretty simple. We can consider adding an I column here, where this will be I 0, 1, 2, 3, 4, 5, 6, 7, and 8. It's important to note that with the trapezium rule, you always start with I equals 0 as your first value. The reason is we are measuring the number of intervals between, and you need 2 data points to get a single interval. So we've got 1, 2, each time we move up, we've got an interval. Anyway, so that means that we have got 8 data points utilizing an h equals 0.1. Just so that you understand, if we were using 0.2, we would be skipping out every second point, and we'd have 1, 2, 3, 4 for 0.2, and 1, 2 for 0.4. So in this case, for 0.1, our n we can state is equal to 8, because we've got 8 intervals. The next step is setting up the equation, and we know from our notes that the equation is going to be from a to b. Those are your first value and your last value of x of your equation, which is f of x, which in this case we aren't given the x. We have been shown it over here, however. And that is going to be equal to h over 2. You might have a slightly different formatted version of it. This is how I like to put it together. But h over 2, then f of x0 plus f of xn plus 2 brackets f of x1 plus f of x2 plus, and we keep going until we get to f of xn minus 1. And that is our equation. It's pretty much simple as that. So in this case, we've been told h is 0.1, so I'm going to put that here, h equals 0.1. So that means that we know what our h is, we know what our f values are, and that's all that's to it. So it's just a matter of substitution. Oh, we also know what our a and b are. That's also an important one to note. We know our a and b from here and here. But going back to the equation, we would simply state with that we'd have 0.1 as our h over here, divided by 2, open brackets, f of x naught is over here, which is 1.543 plus f of xn, our last value, 3.107 plus 2, and then we'd include all of these other values in there. So I'm just going to put the first couple, 1.668 plus 1.811 plus, and it goes on until finally we get to 2.828. And if we punch that into a calculator, we should get something that's approximately 1.7683. And that's as simple as the composite trapezium rule is when you have a set of given data. As I was saying, 0.2 and 0.4, it's just a matter of redoing your i's, because if you're doing 0.2, you'll have 0, 1, 2, 3, and 4, and you'll just be straight up ignoring these columns. But let's look at our next question. Now we're going to look at our next question, using the composite trapezium rule to find the area enclosed by two curves, y equals e to the x and y equals 20 ln x. Now, we know that when an area is enclosed by two curves, that means that they have to intersect at two different points. And we're looking at the area contained between those 2 points. It's telling us, assume that these two curves intersect at this over here. So what they're giving us is an x and a y coordinate, and an x and a y coordinate. So we have x and we have x. Now, I'm going to also highlight these other two terms over here and over here. But it's important to note the more important of these two values is our x coordinate that we will be using. Finally, they state we must impose an accuracy of epsilon equals 10 to the minus 1. Now, first thing that we need to do, we need to go and see, okay, let's make sure that these two curve intersection points are correct. So what we can do is we can state if they intersect at that point, we would then know e to the x is equal to 20 ln x. And we can use our calculator to solve this. If you're not familiar with the Newton-Raphson method on your calculator, I recommend you look it up online and see how it's done. There should be a number of videos on that. But when you do that, you will find that you land up with an intersection point of 1.1759, which validates this. And if you choose a different initial start point for your Newton-Raphson method, you can find a 3.1268. Newton-Raphson's the easiest to do it, but you can do it by various other methods as well. But that validates these two terms. That's great. So the next thing that we need to do is we need to start setting up our equation. We need to get it into the form that we're familiar with, such that we are looking at an integral from a to b of f of x dx, and that has got to that's going to equal what we have, our whole equation, which is going to be h over 2. I'm going to say approximately equal to. It's going to equal h over 2, and then we're going to have f of x naught plus f of xn plus 2 f of x1 plus dot 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 f of xn minus 1. So this is the setup that we need to get into. In order to get to this, we need to know our different values. We've already been given some values, which is quite useful. We have been given 1.1759, which is going to be our A, because that's our start value. We've been given 3.1268, which is our B, our end value. Now we need to find out what our H is. Our H is going to land up being defined with reference to the epsilon. So that is our first point of call. We need to find out what is our H, and in order to find out our H will also inform how many values of n we have. So important things we need, just to note, we need H and n. So that's what we're going to aim to try solve. So we can do, starting with these values, what we need to do is start determining starting with these values, we know that we have our As a start point, to figure out our h and our n, we can utilize our other equation which helps define us things in terms of our epsilon value. And that relationship we know is our capital delta absolute value is equal to h squared over 12, open brackets, b minus a times m. And that has got to be less than or equal to our error value, epsilon. Just so that we can keep things nice and clear, I'm going to make it highlight our epsilon over here, because that is something that we know. we know what our B is, and we know what our A is. We need to figure, and this is going to figure out our H, that's our objective, and we need to figure out our M. Now, our M, if you're not that familiar, our M is defined to be the maximum between A and B. So let me just pull down this a little bit. This is, by definition, it's the max between A and B. That is our interval. I'm going to put that in square brackets because it's inclusive of A and B. The maximum of our function of A between A and B of our second derivative d squared by dx squared of f of x. This is by definition what we're looking at. And bear in mind that we also have to be considering this as an absolute value. So first step is, what is our f of x? Well, we have already defined we've defined that we want to find the area enclosed by them. So we can state that our f of x is going to be equal to 20 ln x minus e to the x. And that will give us our enclosed space. So we've got our f of x. In order to find what the maximum at this is, we know that by definition, a maximum on with a function will occur at either one of the boundaries, or it will occur at where the derivative of the function is 0. And that is from our first derivative test. So I'm just going to put f dt. First derivative test, where we know that we have a turning point, and that is either going to be a maximum or a minimum. So we need to check both of these. Given our equation f of x equals 20 ln x minus e to the x, just double check our equation, 20 ln x minus e to the x, we can therefore state, just by inspection, f prime of x is going to be equal to 20 over x minus e to the x. F prime prime of x is going to equal minus 20 over x minus e to the x. And our third prime is going to be f3 prime x equals 40 over x squared minus e to the x. So let's start with the derivative of the function. We want to know when this term equals 0, and that's quite simple. We can just go 40 over x squared equals e to the x. Either we can ln both sides and treat it like a power 3 equation, or we can just use a Newton method to solve for where our intercept is. I'm going to just use Newton, plug it into my calculator, and we come out with x equals 1.847. And if we plug this value over here, we take that and we plug it into f prime prime of x, we'll end up getting approximately 12.2034. So now we have our first term, first of 3 terms, because we now need to check our boundaries. So let's check our boundaries. Checking our boundaries, this is just going to be plugged into the second prime, so f prime prime of, in this case, we're going to be saying a is equal to, let's just pull up, our a we know to be 1.1759, and that is going to be minus 20 over x squared, so that's 1.1759 squared minus e to the 1.1759. Plug that into our calculator. We'll end up getting, it's going to be negative, but remember we're looking for the absolute value of this for our max. That will come out to 17.705. We do the same f prime prime, this time of b, and that's going to come out to minus 20 over, and our term over here is 3.1268. 3.8 squared minus e to the 3.1268. Plug that into our calculator, we get 24.8465. And when we look at these, we can tell that our options are either going to be 12.2, 7.17.7, or 24.84. We can see that this one is the biggest, therefore that is going to be our max. So now we have satisfied our m equation. So we can now state m is equal to 24.8465. We've now got an m. Let's bring down the equation that we had before and see what else we need to fill in. Bring this down. We can now, let's use our highlighter to show what we've got. We've got our m is equal to this term over here. So let's highlight that over there. So now we have everything except our h and our delta, but we don't really need that in terms of this relationship here. Now it's an important point to note that this over here is not an equality. We have an inequality over there, so we need to maintain that. So what we'll end up saying is h squared over 12 b minus a m less than or equal to epsilon. We can then rewrite that as h squared less than or equal to epsilon over b minus a times m, and we bring the 12 up to the top. 12, we can then square root both sides. And when we substitute our values in, we'll end up with the square root of 12 times 10 to the minus 1 all over b minus a, which is our 3.1268 minus 1.1759. And that is going to be multiplied by our m in the denominator, and we know our m from above is 24.8465. This is all in the square root. Just for clarity, I'm going to do some highlighting. So we have our m over here, m over here. We have our b, which is this over here, this over here. We have our epsilon there and there. And we finally have our a. Our a is over here, and our a is over here. Doing that, we can plug that into a calculator, and we can then state h is less than or equal to, and it should come out to approximately 0.1573. Note that this is still an inequality. We still need to do one more step in order to determine what our h is going to be. So taking this into our next equation, we know that h, which is our difference between our terms, is going to be equal to b minus a over n. We have b minus a over the number of terms, where we also know that n is an element of the integers. So if we substitute this in, we can also state, remember that h is less than or equal to that. So if we have that, we'll just be changing the direction because we're putting the number over here. So we have 0.1573. We can just move this across. So we now have 0.1573 is greater than or equal to b, which is 3.1268, minus 1.1759, which is our a, all over n. Just for clarity, we have got a over there, we've got b over here, and this term over here is what we brought in from above, over to there. We start solving that, we can move the n up to the top, over here, and we can move that number down to the bottom, and we can come out with n has got to be greater than or equal to 12.4, it goes on, but 12.4. because n is an element of z, the integers, we can then state that we want the smallest possible number, so we can now state n is equal to 13. We don't have an h value yet. We have an inequality for h, so we just go right back with this. So we know that h is equal to b minus a over n. We now know n. We now also know b and a. So 3.1268 minus 1.1759 all over n is 13. We can come up with an accurate value for h now, which is 0.150069, and it does go on, but I'm going to stick with this. Something important to just double check yourself. You know that h has to be less than or equal to the term that you defined here. You can just look at this term and check, is it less than that? If it is, then you're probably on the right track. With this in mind, we now have our h, we now have everything that we need to do what we need to do. We have our f of x, and it's simply building that table. So you'll have ix, and f of xi. So I'm going to do the first couple, so I'm going to do 0, 1, and 2. 0, we know, well, that is going to be our a, so we're going to have 1.1759. Now remember, our f of x is equal to 20 ln of x minus e to the x. That is our f of x. So you just plug it into your calculator and you check your answer. We also know that this answer should be 0 because it's where they intersect. Take our next term. We're just going to take this term and add our defined h over here, and we should get roughly 1.3259. Plug that into the calculator, and we land up with roughly 1.8770. I'll just do one more. Again, add h to that. We have 1.4760, and we should get 3.4116. Anyway, you do this for all your terms up until your n. And remember, our n in this case is 13. We know that that should be that should be 3.1268, and we know that our term below should be 0. Once again, now we have our data. Now it's exactly what we had in the beginning. It's just plugging these things into our formula, which lands up being h over 2, open brackets, f of x naught plus f of xn plus 2 times f of x1 plus f of x2 plus keep going until you get f of xn minus 1. Close brackets, close brackets. Substitute all your values into that, use your calculator, and you should get a number that is approximately 8.8465. And that is the trapezium method. Hope that helps, and thank you.